Welcome to Part 1 on complex zeros and the fundamental theorem of algebra. In the previous sections, you've learned that an nth degree polynomial function can have at most n real roots. Notice that I said at most n. In the complex number system, every nth degree polynomial has precisely n zeros. This is because we can include the complex or imaginary zeros in our factorization. If we look at the complete factorization theorem, if p of x is a polynomial of degree n greater than 0, then there exists complex numbers a, c sub 1, c sub 2, all the way down to c sub n, with a not equal to 0, such that p of x equals a times the binomial x minus c sub 1, x minus c sub 2, etc., all the way down to x minus c sub n. Notice that the complex numbers correspond to the second value in the binomial factors. Remember that the n zeros of a polynomial function can be real or imaginary, and they may be repeated. Remember, because of the multiplicity. So we'll just make a note here, multiplicity. Every polynomial of degree n greater than or equal to 1 has exactly n zeros, provided that a zero of multiplicity k is counted k times. Find all the zeros of the following and write the function in factored form. Our first example is p of x equals x minus 2. This is of degree 1, which means that x minus 2, when set equal to 0, will give a root or 0 at 2. So there is 1 0 and it is at 2. In example B, we have q of x equals x squared minus 6x plus 9. Let's see if we can factor that. We'll have an x and an x, a minus 3 and a minus 3. This means that we have a perfect square trinomial that can be written as x minus 3 quantity squared. That means that there is a root, or 0, at x equals 3 with multiplicity 2. This means the behavior at 3 will be a bounce, either upwards or downwards at that point. Since our leading coefficient is positive, it will be a parabola opening upwards, centered about 3 because of the multiplicity. Let's look at example C. F of x equals x cubed plus 2x. Well, I see that I can factor an x out. That will give me an x squared plus 2 inside parentheses and an x outside. If I set each one of these factors equal to 0, I will have x equals 0 and x squared plus 2 equals 0. If I solve for x, I will get x equals the square root of negative 2, which is equivalent to I root 2. Remember that the square root of negative 2 is equal to the square root of negative 1 times 2, where the negative 1 is equivalent to I if you bring it outside the radical. Also, when you impose a square root on both sides of an equation, you have to keep the plus or minus sign because it's an even root. So this will be x equals plus or minus I root 2. So if I wanted to list all the factors of f of x would equal x times x minus I root 2 times x plus I root 2. Notice that the degree is 3 on the f of x, and there are 3 distinct roots. Let's look at our last example where we have x to the 4th minus 1. I know this will factor because it appears to be a difference of something to an even power. If I factored it, I would get x squared and x squared, a plus 1 and a minus 1. If I broke this down further, the x squared plus 1 would not factor further, so I'll just drop that one down again. But the x squared minus 1 would factor to an x and a plus 1 and a minus 1 because it's a difference of squares. So when I look at my x squared plus 1 and I set that one equal to 0, solution off to the side, x squared plus 1 equals 0. Therefore, x squared equals negative 1. If I take the square root of both sides, again, I have a complex solution. I get x is equal to plus or minus I. If I write the final solution g of x in factored form, I will get exactly 4 roots. I will have an x plus 1, an x minus 1, an x plus I, and an x minus I. Therefore, my zeros of the polynomial are x equals negative 1, x equals 1, x equals negative I, and x equals positive I. Those are the 4 zeros of my polynomial. This is my polynomial g of x in factored form. And to find the zeros of the polynomial, all of them, I set each factor equal to 0 and solve for x.